We are now going to try and take what you observed in the balloon lab and apply it to Newton's second law of motion. So let's review a few concepts, and then we're going to develop some very simple math equations. First, if the net force is 0, we say that the system is balanced. Check out this picture of a man balanced on a rock. I want to see you balance in that particular position. We know that a system is balanced because the object will not accelerate. We talked a lot about this on Monday when you learned about Newton's first law of motion. Today, we're going to look at what happens if the net force is not 0. If it's not 0, we say the system is unbalanced. Look at this poor donkey on his unbalanced cart. We know that a system is unbalanced because the object will accelerate. In other words, the velocity of the object will change. It's going to speed up, slow down, or turn. In the balloon lab, we saw that there were two variables that influenced the rate of acceleration. You changed the force of the balloon by changing how much air pressure you put inside the balloon. You also changed the mass of the balloon by taping heavy metal washers to the bottom. Both of these changes should have influenced the behavior of the balloon. Now, in a perfect world, you should have seen that more force moved the balloon faster and more mass moved the balloon slower. If you saw something else in your balloon lab, then it just means that your balloon was not cooperating, but hopefully you observed these patterns. What this means is that acceleration is directly proportional to the net force. Remember that directly means that both variables do the same thing. So if you have more force, you will also have more acceleration. I don't know why this sentence has an extra blank at the end. That's a typo. That's not supposed to be there, so you can scribble out that blank at the end. What this means is that if the net force is twice as big, the acceleration of the object will be twice as fast, or 2 times faster. This very much follows common sense and what you've experienced in your own lives. The harder you push something, the faster it goes. On the other hand, acceleration is inversely proportional to the mass of the system. Inversely means that the variables do opposite things. As the mass got bigger, the acceleration of your balloon should have gotten smaller. This means that if the total mass is twice as big, the acceleration will be half as fast. Notice that we divided by 2 instead of multiplying. These two patterns that you're looking at summarize Newton's second law. Let's try applying it to a very simple example, and I've provided pictures to help you visualize what is happening. So we have these trains, and the engine car represents force. This is what pulls the system forward. And the other cars represent mass. This is the load that the train is trying to transport. In the first picture, we have one force car and one mass car. And then we are told that the acceleration is 12. This is just a number that we have been given. If you look at the next train, it has 2 force cars and only 1 mass car. Our job is to try and predict what the acceleration of this train will be by comparing it to the first train. It's pretty easy to see that this train has twice as much force as the original train. And so based on what we've learned today, we expect it to accelerate twice as much. That means we need to take 12 and multiply by 2, which gives us our new predicted acceleration, 24. What I like about Newton's second law is that the math is so friendly. All we're doing is multiplying or dividing. The next train has one force car, but it's carrying two mass cars. Once again, we need to predict the new acceleration. This train has twice as much mass as the original train. So, based on what we've learned today, we expect it to accelerate half as much. 12 divided by 2 equals 6. Notice that with mass, we divide to get our new value. The next train has 2 force cars and 3 mass cars. So we've made 2 changes, but we can still predict the acceleration as long as we acknowledge both of the changes that have happened. This train has twice as much force and 3 times as much mass if we compare it to the very first train. I'm going to start with just the force. So I'm going to multiply 12 times 2, and that gives me a value of 24. However, I also need to acknowledge that the mass has changed. And so I'm now going to divide by 3, which gives me my final answer. I would expect this train to accelerate 8 meters per second per second. So if both the force and the mass change, you just deal with them one at a time, and you'll still get to the final answer. Our last train has 1 force car and 4 mass cars. We need to predict the new acceleration. This train has 4 times as much mass. So what we are going to do is divide by 4. This gives us a prediction of 3. Now, if you're dealing with very simple pictures, you can often just think through Newton's second law in your mind without having to use any fancy equations. Unfortunately, we're going to be encountering story problems that have numbers that are less friendly, and so we need to talk about a more systematic approach using some equations. And the first thing we need to talk about is something called a change ratio. The word ratio means to divide, and so a change ratio, we take the new value and we divide it by the old value. The change ratio can be used to help us make predictions for Newton's second law. If the force or mass in a system changes, then so will the acceleration. We saw this with the train examples that we just looked at. Now, the changes are predictable, and we can use an equation. If you want to know the new acceleration, then what you need to do is take the old acceleration, multiply by the force ratio, and divide by the mass ratio. Let's look at a few examples of how to apply this, and you'll see that it's not that difficult. Oh, I forgot to mention, if a ratio is not given, then the ratio equals 1. Basically, a ratio of 1 just means that that variable stayed the same. Our first practice problem says that the acceleration of a brick being pulled by a string is 3 meters per second per second. What would happen to the acceleration of this same brick if we changed the net force from 5 newtons to 20 newtons. The first thing I'm going to do is calculate my ratios. The force ratio is 20 divided by 5. Notice you take the new force and divide it by the old force. In this case, we get a value of 4. This just means that our force has increased to 4 times its original strength. They didn't give us any information about the mass of the brick, but I'm going to assume that the mass didn't change. This gives us a mass ratio of 1. Now all we have to do is plug these numbers in to our equation. Make sure you put the right number in the right place. The old acceleration was 3, the force ratio was 4, and the mass ratio was 1. Put this together, 3 times 4 divided by 1, and you get the number 12. The new acceleration of the brick will be 12 meters per second per second. Notice, if we compare this to the original, which was 3, that this brick is going to go a lot faster. This shouldn't surprise you because looking at the force values, we are pulling on the brick a lot harder. If you are the sub, please pause the video now and give the students some time to work through the rest of the practice problems. After they have had time to work through all of the remaining questions, resume the video and have them check their work. Here is the answer to the next question. The force ratio is 1, the mass ratio is 10, and when we plug this into the formula, we get a new acceleration of 0.2. Notice this is much slower than the original system. The next question about a rocket has a force ratio of 0.56, a mass ratio of 1, and when we plug it into our formula, we get a new acceleration of 2.24. Notice this is about half the acceleration of the original system. The next question about a jet ski has a force ratio of 1, a mass ratio of 0.2, and when we plug it into our formula, we get a new acceleration of 12. Notice this is a lot faster than the original system.